Flag. Hello, everybody, and welcome to the April meeting of the Howard Astronomical League. I'm glad to see lots of people here in person, especially if I put the right glasses on. And I'm also happy to see all the people online. Welcome. We have a pretty neat meeting this month. We just had some very exciting, there's a lot of activity in the club given the exciting events of recent days. So we'll talk a little bit about that and we'll talk about some other things. So our agenda is, yeah, here we go. Supposed to be able to click my mouse. Okay, that's not really doing what I wanted it to do. Here we go. Okay, so the agenda for tonight, we'll go through some introductions. We have a few announcements. Book of the month. We have a very, very interesting speaker. I'm really excited to hear about the weather similarities, and I know some of our planetary guys would be very curious to hear about some of this stuff too. And then we'll have what's out in the sky this month with Jim Tomney, and then go over some images and sketches. So I went too fast. So is there anybody new in the room or online that would like to say hello?
I'm new. Yeah.
Our speaker, you could, I think we can give you honorary membership in the club for coming and speaking.
I'm Rick.
Yes.
Well,
Yes. Well, you'll hear a lot more from and about Rick shortly. So let's go ahead and move on then. We just had a star party that was pretty successful. We have another one coming up. I'm going to come out into the audience and view it from where you guys are viewing things. Do you mind?
Okay.
Thank you. So we have members star party coming up on June 8th. And sorry,
May 4th.
did I say, oh, I circled the wrong one. Oh, my bad. This is what happens when you do it at the last minute. So May 4th, sorry about that. I'm just off a month or two. I don't know how the heck that happened. That's not even close. Yeah, May 4th, we have a party coming up, which is just in a couple weeks. Also, April 20th and 21st, that's this weekend, are is the NEAF Expo. I know that there's some members who are going up to New York for that. There's a couple of meteor showers coming up, and I don't think these are going to be too good. These are, first of all, you have to get up at like 5 in the morning to see them. And the first one there'll be kind of a full moon. The second one, it's a waxing crescent, but it'll be very, very low in the east sky for the Eta Aquarids. Does anybody else have any upcoming events that I forgot to put on here or would like to mention? Online or in the room, anybody? Okay. Yeah, so May 4th, I have to update that. So we just had our April public star party. These are some photos from the event. We had a great turnout of telescopes. There was 25 roughly, including like 6 or 7 electronic smart scopes, showing all sorts of cool stuff. M81 and AIM-82 were big hits in the observatory, and on my personal scope, we were looking at that. Anyways, it was had about maybe 120 visitors. It was a good time. And we also had an impromptu star party on April 8th for the eclipse. We weren't even really planning on it. At least my plans were very up in the air. And at the last minute, it turns out that I stayed in town. So, and Hannah, also our public outreach coordinator, managed to get the afternoon off. So we opened up the observatory, and there were a whole bunch of people, some from the club and some just members of the general public. At least one group told me they knew the dome was here on the building, so they thought something might be going on. So that's a good sign, a good reason to not have a roll-off roof observatory. Anyways, we had the Eclipse with the white light filter with a nice image. I took a couple of images during the event, and it was a good time. I'm gonna say a little bit, and I couldn't resist showing a couple of pictures, but next month is the meeting that we're really gonna focus on the eclipse. And Jim Johnson is gonna kind of describe the collective HAL experience. Jim, do you want to say anything about this?
Yeah, just a couple words. So the eclipse has happened, it's over with. Many HAL members, about 45 or so, I got information from, so it sounds like we had a good amount of members that got out to see the eclipse. Several for the first time that now understand what the big deal about totality is versus a partial eclipse. So I look forward to sharing that story, some amazing stories that I have, and the collective story of HAL is coming together. It's looking pretty exciting, and I look forward to sharing that with you. I would encourage you to come here to the Robinson Nature Center if you can. It's going to be a very highly interactive presentation, and the difference between being on Zoom and being here will be like the difference between a partial eclipse and totality. So come on out if you can on May 16th.
16th.
16th, yes.
I'll be out of town, and I have a niece that's graduating, so I'll be out of town, so I won't be here, but I'll watch the YouTube recording.
That's terrific, Dan.
Yeah.
Thanks, Jim. You know, you just reminded me, I meant to put the XKCD comic strip in that Wayne linked. I forgot to put it into the meeting slides. The one about.
I haven't forgotten. I
Yeah.
have it.
You have it?
Yeah.
Okay, so we'll have to, I'm afraid to, if I go to my computer and start bringing up a web screen, I'm gonna screw up the display. So we'll have to wait until next month, unless, Wayne, if you want to bring it up, you can share your screen. Maybe not ruin it for Jim though. Anyways, here are a couple of pictures taken by our own James Willingham. And I saw some pictures on the NASA website, and like this picture here is really close to NASA's official, like this is just an amazing photo. And we had tons and tons of them. And if you're on the email list and you haven't been turned off by the volume of emails that we've received over the last few weeks, if you've managed to make it through, you've seen that there are just quite a few amazing photos from members of the club. Okay, so next is Book of the Month.
All right, so hello, I'm Crystal. I run the library collection, and so I chose this month to review The Grand Tour, A Traveler's Guide to the Solar System by Ron Miller and William K. Hartman. So the length of it is about 305 pages. I would say this is definitely beginner friendly. So I took some notes a little bit on the history of the series. So the first edition appeared in 1981, followed by a second edition in 1993, and this edition that we have in our collection, that's 2005. Now you might ask the question, why would I review something that's nearly 20 years later? You know, 2005 was a while ago, but I think history offers some perspective. It's easy to take for granted the stunning imagery and photography that we have so easily accessible at our fingertips. And plenty of people have probably heard, you know, the debate of the realness of an image. You know, is it Photoshop? Is it AI generated? You know, especially after an eclipse, my social media feed was flooded with artificial images that were not true pictures of the eclipse. So I thought this coffee table book offered a great perspective of how far we have come before the dominance of computer editing and software. So this, the book I'm reviewing here, and I'll try to hold it up, has really amazing artwork. So these are paintings, drawings, sketching, really artist depictions of what the view looking at Saturn might look like from, you know, a moon of Saturn, for example. And so I think there's something to be appreciated about the detail of what goes into sketching things or trying to imagine things. And I think we're a little spoiled by how easy NASA makes it now, right? Or, you know, really expensive astrophotography equipment just makes it so easily accessible. So overall, I think it's a great opportunity that there's something for all levels of readers, and I especially found that this had a novel approach, that they went through the order of size through our solar system rather than the order out from the sun. And the reason was to give the perspective of, if there is outsiders coming to our solar system, what would they discover first? Well, they'd notice the sun, then they maybe would notice Jupiter, and then, they wouldn't find Earth first as evidence of our solar system. So it was a different way to approach it. And so overall, I think it just gives everyone a little bit of something. It gives us, perspective in how much photography and our understanding of space and the visual medium has evolved over the last 20-ish years. So even though this was published in 2005, and I haven't found any record that the series continued afterwards, the author Ron Miller has done a ton of illustrations and co-authored many other astro-related books. So if you're looking for a coffee book table where you just want to look at some imagery and gain a little appreciation of how far we've come in the last 20 years, this is the book for you. It's available for immediate checkout if you're here in person. Otherwise, come find me at a public star party.
Terrific.
All right.
Thanks. Okay, so next is our featured speaker. So Rick Cosentino has degrees in physics and electrical engineering from SUNY Buffalo, a degree in astronomy from CU Boulder, and a PhD in physics from New Mexico Institute of Mining and Technology, sometimes shortened as New Mexico Tech, which is very close, my understanding is, to the Very Large Array.
Yeah.
Being an antenna engineer, I'm very appreciative of that place. I love it. He later moved to NASA Goddard for his postdoctoral work, continuing to study Jupiter's atmosphere, including the Great Red Spot and smaller spots and storms. He's also worked on the OSIRIS-REx mission as an instrument scientist, and he's now working in the instrument division at the Space Telescope Science Institute on the Nancy Grace Ronin Space Telescope, which I'm excited about, and the calibration reference pipeline. So without further ado, we can, yes, welcome. Let's see if I can do this.
Well, thanks for the introduction.
Very welcome. If I only had like better audio visual skills, then it would be even better. Let's put the right glasses on.
So while he's getting that, yeah, I brought a bunch of stickers and lithograph swag, if you will, and you're welcome to have anything that you'd like up there.
Okay, I think I need to stop sharing this one first. If I could figure out how to do. So how do I stop that? It's too many menu bars all over the place. No, that's the other, that's the Zoom share. I need to stop the PowerPoint share. Hopefully I didn't close PowerPoint. Does this look like your first slide?
That looks like it, yeah.
All right, do you want me to flip for you?
Oh, no, I can do that.
So you just click the mouse button and that should.
Okay. All right, is this microphone on?
The mic doesn't work. The mic is actually either this one or this one. I'm not sure which one it's working right now.
Can anybody online hear me? Say something? Oh,
Yes, we can hear you.
okay, great. Okay, yeah, so yeah, thanks for the introduction. And one of my colleagues, Brian Holler, I don't know, Victor knows him, suggested me as a presenter one month, and Victor reached out to me and said, hey, would you like to come give a talk? And I said, sure. And this is 1 week before the ALMA deadline, and it's a very busy time for a lot of people right now. But no, this is great. I actually finished proposals early this year.
Wow.
So first time ever. So yeah, I'm going to talk about just weather and clouds in the outer solar system. So just rough outline. I'm gonna start talking about me and the Earth and how I got sort of into all of this. And we'll go out to Jupiter, and that's the planet that I studied the most. And we'll talk about the Juno mission and polar cyclones, and then Saturn, about the hexagon and polar vortices there. And I'll end on something, Uranus, which I've actually just put together as part of a proposal I'm submitting next week for Alma. But please, interrupt, ask questions. Really don't mind. Yeah, so myself, this is a picture of the VLA. I lived out in New Mexico for 6.5 years. I was doing my PhD, and I'm originally from Buffalo, so I went from a place with a lot of water to no water. And yeah, after living in New Mexico, I came to Goddard and worked on the OSIRIS-REx mission as an instrument scientist. And now I have a permanent staff position at Space Telescope working on the Roman mission. I love my job so much because I went into engineering first, but I always wanted to do astronomy and didn't know how to do that at first, but feel like I found a career path where I'm really combining the two. And I think it's the coolest thing in the world. So for the Roman mission, just for people who might not know, this is a new space telescope that's going to launch in 2.5 years. It's basically the size of Hubble, but it's mainly an infrared survey instrument or survey telescope. And so it's named after Nancy Grace Roman, who was the first female NASA administrator. And she, during the 60s, started advocating the need for a space telescope. And that turned into the Hubble Space Telescope. And the workhorse of Roman is the instrument that we're working on calibrating. It's called the Wide Field Instrument. It's over here on the right. And it has 18 4K by 4K detectors. When we were talking about field of view earlier, so this is a little comparison to show you how Roman is different than Webb and Hubble. So Hubble and Webb, their field of views are there, and Roman is going to look at 100 times more size, or 100 times the field of view that those can do. And so this observatory in the mission is to cover large patches of the sky to answer questions like, well, what is the dark energy distribution and galaxy distribution throughout the large portions of the galaxy. And so it's a lot different when you think about Hubble and you think about Webb. We're looking at specific targets. Roman's not going to do that. It's going to go look at large portions of the sky all at once. Do you have a question?
No, I was just picturing the 18 little squares that make that up.
Oh, well, yeah.
I have a question, actually.
Oh, okay.
It's maybe premature to jump in a question now, but how you gonna get all that data down?
Okay, well, we'll get there. So, great, yeah. So, Roman is also, because it's big field of view, this is the age of large data, and this is big data. And so this is where astronomy, like particle physics and some other branches that you hear about in STEM, we're entering this new era. And so you can see the field of view. So there's Andromeda, that's M81. And Hubble, to look at the entire Andromeda galaxy might take years to do something that Roman could do in a couple pointings. And if you want to talk about data, so our downlink, we're going to be using the Deep Space Network. So there's 3 dishes that you get. I don't know the exact, I think it's like 14 terabits a second or something. But you can see the entire Hubble archive for 30 years is that small square. Webb, after 5 years, is that yellow square. And this is what Roman is projected to get. And to let you know right now, like we are in our vacuum thermal chamber testing, and we have about 1/3 of all the Hubble data just from testing. So the data volume on Roman is going to be astronomical, if you know.
I just want everybody to know, I did not see these slides in advance. When I asked that question, I did not know this.
But let's talk about some science. So yeah, Earth is my favorite planet, and a lot of people ask me often, what's your favorite planet? And it's Earth, and I study the atmosphere. So one of my favorite things to do when I'm on planes, I didn't take this picture, but I like to look out at the clouds because everything we're going to talk about now is what we can learn about clouds from the other planets. And my PhD specifically focused on waves. And this is a picture of waves in the atmosphere. So waves, like in the ocean, they carry momentum and energy. And when they break, they deposit that. You can get knocked over at the beach. Certain processes, similar processes happen like that in the atmosphere. And that's sort of what I studied.
I believe that's what meteorologists call gravity waves.
Yes. Yeah, and those are different than gravitational waves that come from black holes. So real quick, so this is the famous picture from the Apollo missions looking back at the Earth. And what you see here is like you can see where clouds are and the shape of the clouds. And from like just taking a snapshot of this, thinking about how we use Hubble to look at the other planets, you would never sort of get from one picture that you would say, oh, well, obviously there's a continent underneath at the South Pole there. It's all dominated by clouds. And you could see where, oh, there's some green and orange, and maybe you can infer that there's like differences in surfaces. But would you understand that like the circulation, large scale circulation is dominating where rain falls and what's going on with the clouds there? So what we have a lot of times is I have some cool animations here, but a lot of everything that we look at with the planets is just single snapshot. Okay, so Earth's atmosphere, I'm going to be talking mainly about Jupiter and Saturn's troposphere. So this is at the ground level going up. This is where all of your weather happens. This is where we live. 90% of the atmosphere's mass is in that first layer. But the stratosphere, the area above that, is intimately connected to the troposphere. That's where we have the ozone layer. And that's where the planes fly. That's where you get out of all of the turbulence and weather. You go fly up in the stratosphere. The outer planets don't have as well-defined of a mesosphere. You'll see that in a little bit, but just to let everybody know, if I'm talking about troposphere, stratosphere, sort of the relationships of where things are, it's all related to this temperature structure and relative same pressures. But okay, so can I get my water? Excuse me. Thank you. So I love this picture because it shows all the outer planets. And I've actually, so for here, I put all of the answers down there. But what you should look at this is realize that we can tell a lot of science just by these pictures here. And we can look and see that the planets are different sizes. And those sizes vary as a function of distance from the star, from our sun. The color changes as a function of the distance. Also the contrast, like Jupiter, you see this well-defined features and banding. And then as you get further away, Saturn is starting to become a little hazier, but it still has some banding. By the time you get out to Uranus and Neptune, basically fuzzy blue balls. You can see here that the great red spot is clearly visible. Neptune has some storms in this picture here, but like Saturn has the rings and you can see it's obviously tilted, but Uranus is tilted almost on its side. You can't really notice that from this picture. And also the discovery in which they were found, Jupiter and Saturn were known to the ancients, and we didn't know about Uranus and Neptune until telescopes were invented. And Herschel found Uranus in 1787, and then Neptune was like 100 years later. So there's a lot of science that you can learn just from this one picture here. And so why do I study these planets? Like that's what everybody will ask is why study Jupiter? Well, Jupiter is the closest and it's also the biggest and it doesn't have all that haze. So we can see a lot of the features and as they evolve in time. And it's all because, and I promise this is probably the most complicated plot we have here, is that clouds form at different altitudes and at different temperatures. And Jupiter and Saturn are close enough to the sun that that methane cloud that you see there at around 100 Kelvin doesn't form as much as it is at the outer planets of Uranus and Neptune. And that's what really obscures our view. And so these different cloud layers are sort of what we're seeing. Okay, Jupiter. So I didn't know we were going to have a book review about. So yeah, Jupiter is was it 10 times the size of the Earth in radius? It's 1,000 masses. There's lots of factors of 10 here. It rotates every 10 hours. It doesn't really have seasons. So the tilt of Jupiter is around 3 degrees. We are 23.5, I think, or so. And Jupiter is 5 times the distance from the sun than we are. So it gets 1/25th the amount of energy that we get. So, but when we see all of this, is like we see a lot of storms. You see the great red spot here. You see all this convection happening. And so obviously there's a lot of energy left over from when it formed. And a lot of this energy is coming out and driving all the weather that we see. Okay, so we talked about Jupiter's vertical structure here. In general, I just want to make sure everybody understands like the upper cloud layers are the troposphere, and we're going to go deeper down. But a lot of the area that we don't have on Earth is anything below or greater than 1 bar of pressure. So there's no surface on the gas giants. Everything just keeps getting deeper and more pressure. And that's a big difference between the weather that we see on Earth versus the weather that we'll see on the other planets. Okay, so everybody here is familiar with filters. And so when you look at Jupiter with like the Hubble Space Telescope and a blue filter, you see certain features pop out. And what we do with these, just like everybody, I think, imagine you want to make a red, green, blue image. So here's a green filter. And if I go between the two, you can sort of see what bands and what clouds are sort of popping out. And when you look at the red, there's a noticeable difference here. So what we like to do sometimes, and what I've done in the past, is I'll take the difference or the ratio of the red and the blue to increase the contrast as much as possible. We get like sharp definitions of where the clouds are. And we do that for like the great red spot to measure its extent, and these small little spots here and the waves that you can see there. And so you stitch these together and you can make like a true color image. Something that I've learned over time is that probably we are over exaggerating the orange in Jupiter. It's probably more brown, muted. So a lot of the red that we see is probably not what it really looks like if you were to go up close to it, but it's still, you can see a lot of features in here, different colors. And if we go deeper in wavelength or longer in wavelength, we're looking deeper into the atmosphere. And so if I go back, I want you guys to notice, especially, and this is gonna be hard if they can't see online, but this region right here, right? So this is the equator, and right above that, do you see these like dark spots?
Mhm.
Okay, those spots there are sort of areas where there's not a lot of clouds. You don't see any white wispy clouds there or even red. And so when I go to this next image, these are where these hotspots come. So these are called these 5 micron hotspots because they're really bright in the infrared here. And this is a Rossby wave. It's a wave, it's a sine wave of going up and down. And that's where you see. So the hotspots are actually troughs in the wave where there's no clouds. And then the crest of the wave has some cloud cover. And when you're looking deeper into the atmosphere, it's warmer. So when we look at Jupiter, you see all this banding. And the banding, the most simple model that we can come up with here on the left is that the zones are these white areas. And we think that that's where convection is happening underneath. It's bringing material from deeper down to higher altitudes. and that material is whiter, and that the regions next to it that are darker, the belts, are areas of subsistence and downwelling, and there's no clouds there. So we're actually seeing deeper into the atmosphere. This model is like pretty simple, and it does a pretty good job at approximating, I think, the vertical motion. But obviously, theories could say that, oh, well, there's multiple stacked cells and vertical motion happening at multiple areas, because on the right, you can see that the banding sort of follows this wind pattern. So the equatorial winds are the fastest. And when it's going to the east, you have all of these zones. And when it's going to the west, you have the belts. But we only have observations of lightning in the belts. And lightning is associated with convection and thunderstorms, right? So over there, the thunderstorm should be happening in the zones, in the white area, but we only see the lightning in the belts. Does that mean that there's no lightning in the zones? Or is it because the belts are going down, is that maybe we're observing lightning signatures happening deeper in the planet, where convection is happening deeper, but we only can see down there because there's no upper level clouds? So it's really interesting. If I say something that is a question, we really don't know the answer. Like, people will have varying opinions. Yeah.
So this velocity, left and right, positive and negative, does that change over time, or is that mostly usually the same?
So really good, very good question. Paper 2017 I was on, we found that the strongest jet isn't at the equator. It's at 25 north there. And that jet changes speed. And the cloud morphology in that area is correlated to changes in that velocity. It's probably one of the most cited papers that I've been a part of. And trying to figure out why that happens is like a really big question. People are trying to model and understand that.
But the directions are always
The directions are basically the same, and I don't have it, but like, this is an average. And I would say if you were to look at it, it hasn't changed since we've been measuring it.
Okay. And at the spots where is that where all the swirly stuff is? At the spots where it crosses?
Yeah, at
Left,
zero.
at
Yeah, the
zero.
inflection points there are where the storms are, and this little kink, yeah, like in between here, right there, that's where the great red spot is.
Cool.
So it's sitting right in between opposing jets. We'll get to there. So this is actually an image I made using the VLA of Jupiter. And that was the point of me going to New Mexico, is I wanted to work and use the VLA. And so this is radio emission. So we're looking at differences in temperature. And like I was saying, the different areas in Jupiter's atmosphere have different cloud layers. So if you could see deeper down, it's going to be warmer versus cooler for high altitude clouds. And this is a really cool image, but if we actually make a map of it, this is what Jupiter looks like in the radio. And you can see here, remember that area I was telling you about, the hot spots? You see these red alternating patterns here. And you can see on the left there, the great red spot. And I don't want to get into what all of this means, except that before the VLA was upgraded in 2012, we couldn't do something like this. The instrumentation and the sensitivity wasn't high enough. So this was something that was capable when I was out there, luckily doing my PhD, and I said, I have an idea. I want to study turbulence. I want to look at structure of Jupiter's atmosphere with the VLA and compare it to Hubble. And then I was able to take that map and I'm going to make a little globe and have it rotate and everything. So I just think this is one of the cool like animations I'm able to make here. But okay, so everybody here is taking pictures of Jupiter, I'm sure. And I thought what was really cool is I was able to figure out ways to do this study of Jupiter's dynamics and then use amateur astronomers and their pictures, because the Hubble telescope isn't looking at Jupiter all the time. And so on the top here, I have like an optical image from an amateur, and the very bottom is also another one, and there's a separation of about like a week. And my VLA observations are right in the middle. And what we're able to do is, like, if you see these little features labeled like P1 and V2, that I'm actually able to go and find these a week later in the two amateur images, and then correspond it back to what I saw in the middle there. And we extracted wind velocities and talked a lot about these plumes here and the structure of these hotspots in more detail. But this was a way that like amateurs for Jupiter really give us a lot of like valuable information.
A question.
Yeah.
So what sources are you using for amateur pictures? So, where do you find these amateur pictures that you make use of?
Okay, if you want, you can send me an email. I have these repositories marked, and there's a couple, there's one website, I think hosted out of Japan, that has maybe 3 to 5 major contributors. I don't know their names off the top of my head. I have it in my paper, but no, there are people that look at Jupiter like in Spain and in Japan and a couple other people, and they take pictures of Jupiter every day. Same filters, same setup, and sometimes, through lucky imaging, they get really, really good pictures. And we can go there and look. And a lot of well, I won't say a lot, but some astronomers like go to that as looking for evidence of comet impacts. And that's actually one way that we've seen other impacts that weren't detected by like major NASA facilities, is because amateurs are taking pictures on a regular basis. But if you send something in the chat, I can share more info with you later.
Sounds good. Thank you.
Yep. And then this is another one. Another way I was able to use amateur astronomers here is actually 3 different amateurs. I sort of stitched together this bottom map here of the region with the great red spot. And so in the VLA data in the top here, you can see this noticeable asymmetry, but that the VLA is sensing deeper in the atmosphere. And so Hubble, or the amateurs, like you're confined to that upper cloud cover of the great red spot. But you can see here that these smaller spots over here at the bottom, like they don't show up that great in the VLA data, but this region over here, like this hole that's in the radio data, you can't see it at all. So what cleared that hole deeper down in the atmosphere? What happened there to make something that was so deprived of any cloud cover, but then didn't go up all the way to the upper cloud layers? And so this is the sort of questions that I've been studying for a while. Okay, so the Great Red Spot's not a hurricane, it's an anticyclone. Hurricanes on Earth are cyclones. So the Great Red Spot is at 22 south. Its winds are about 500 miles an hour. It actually oscillates in position every 90 days. Gravity waves come from hurricanes and the Great Red Spot. So we see evidence of this when we looked at really, really strong hurricanes like Hurricane Maria. When that hit Puerto Rico, you can see these gravity waves oscillating away from it. The Great Red Spot has evidence of gravity waves above it. And so, yeah, it is not a hurricane. You can see over here that asymmetry again, about temperatures and how cyclones work on Jupiter is not exactly what we would expect for the Earth. And this is sort of like a diagram of what's going on. Here is that there's a hot spot at the very bottom, and it's tilted a little bit in latitude. And there's a cold layer on top of this. And when we're looking at all of this, we're sort of seeing like this middle region that's swirling around. And you can see this like idea of, well, there's not just one Hadley cell. There's not one cell of vertical motion. There are multiple. And that's what these blue arrows are sort of showing here. But now this is probably, I The black lines didn't show up. Okay, shoot. No. Oh, there they are. Okay, cool. So the great red spot shrinking. And the story of this is like I studied turbulence, and my advisor is Amy Simon, and she said, okay, the great red spot shrinking, we know this, but I don't know why it's changing color. And so here you can see pictures from, was this 95 to 2014, how much it shrunk. I remember everyone said it was all 3 times the size of the Earth. Now it's only about 1.5 times the size of the Earth. But because I told you I study turbulence here, so I just want to talk about this real quick, is that I feel like everybody has seen clouds, and you've seen stuff that looks like on the left and in the middle and on the right. You've seen different cloud distributions. And from turbulence theory, based off of the spatial distribution of clouds, you can sort of tell how much energy is flowing in and out of a system. And my advisor, she asked me, figure out why this is like happening, but I was also reading a book about turbulence and vorticity at the time, and then I had this idea. And so everybody knows that ice skaters and angular momentum, I think everybody's familiar with that. As you bring your arms in, you're going to spin faster. And the great red spot shrinking, but when we measured all of the winds over that time frame, the velocities stayed the same. And so something needs to be conserved, and fluids don't have angular momentum. They have something called vorticity. And so vorticity needs to be conserved. And the only way that that could be conserved is, I found this GIF here. Vortex stretching was the answer. And it was in this book. And it's how hurricanes and tornadoes, when they start spinning up and they get faster, they sort of vertically extend higher into the atmosphere. So I said, it's got to be getting taller. So I just didn't say this, and then we wrote a paper, said it, but we did a lot of math, and we came up with some models and found something, and it's probably one of the coolest moments I had for like an hour there. She was in a meeting, and I'm like, I think I got something. And like, I think it's getting taller. And we started going through, and it turned out, yeah. So that was one of the coolest things I probably found in my life. So here's the great red spot from the Juno mission. You can see all this great detail from Juno. Like, it flew right over the great red spot, I think, for 3 parajoves now. So we got really accurate measurements and pictures like this. The Juno cam image, or the Juno cam on there, I don't know if you guys know this, but it was actually not in the original mission design. And somebody said, why we can't send a probe to Jupiter without a camera? They said, oh, we'll put a webcam on it and let the public decide what it looks at. And then we got pictures like this. Yeah.
What is a parajove?
Oh, I'll get there in a second. So parajove is when we sent Juno there, it's in a 53-day orbit. And these blue lines on the end there are of the orbit of Juno going into Jupiter. And so the parajove is its closest approach to Jupiter. Yep. And so you can see these, like the orange or the green and blue circles here. Every time it goes in, it's sort of through gravity and general relativity, it sort of shifts the orbit a little bit. And so we actually are able to map all the different longitudes just by having it processed. And the reason why you have to go in there is because this is the magnetic field of Jupiter. And if you wanted to look at longer wavelength radio emission with like the VLA, this is all you'd see. So when Juno went there, in order to do the measurements it wanted to do, it has to go inside of that orbit of that band there. And so for Earth, we have these like Van Allen belts. That's what Jupiter has, but its magnetic field is so much stronger. And so we can't observe at certain radio wavelengths anything deeper. So Juno actually goes through this radiation, goes inside of it, and is able to look at something that we can't do from the ground. But it's also getting healthy doses of radiation poisoning every parajove. Here's a sequence of pictures from the Juno mission. And what I think is really cool is when you look at this image over here on the left, and really zoom in, what you're seeing here is these are high altitude, like icy snow clouds. Like these are the tops of like probably very like strongly convective cumulus convection happening there. And this is like ice crystals forming that we see here on Earth. And then also the one thing that JunoCam found is these polar cyclones, these images over here. So this is actually an animation showing, because the Juno mission is rotating, we have to stitch all of these images together. There's a stable one coming up, but we've never seen Jupiter's poles before because it doesn't have any tilt. So the only way that we've ever seen the poles of Jupiter before, or the only way we've ever been able to see the poles of Jupiter, is from the Juno mission. And so both of the poles exhibit these weird polar cyclones. And this is what it looks like. This is the north and south pole of Jupiter. And you have these large, at the North Pole, there are 8 cyclones. And in the South Pole, there are 5. I don't know why. And people are trying to figure out why. I mean, it could be a wave sort of thing. But this is something that we never saw before. And nobody really, I think, anticipated it until Juno got there. All right, so let's go out to Saturn and talk about the hexagon. So Saturn's a little bit further than the sun, well, a lot further, but it rotates around the same. It rotates like every 10 hours. But big difference here is that Saturn has seasons. It's seasonal, like its axial tilt is more similar to the Earth. And it has it has the rings, and everybody loves the rings. And the rings actually have been a sort of an interesting laboratory. When Cassini was there, you could actually see waves in the rings, and that is from oscillations within Saturn's core. And so the rings were actually acting as like a sort of experiment for us to figure out what's happening in the core. And that information then, when people applied that model then to like Jupiter and the other planets. So these rings are, and I think the rings are only what, like maybe 300 or 250 million years old. So imagine like the first dinosaurs, Saturn didn't have any rings. So the hexagon at the top at 78 degrees north is something, it's actually just a sine wave, but it's a sine wave that is forced onto a sphere. And so the sine wave has 6 troughs and peaks, but when you project that onto a sphere at that latitude, it looks like a hexagon.
In polar coordinates, it's a sine wave.
In polar coordinates, it's a sine wave, yeah. And so this is a little animation of it. So you can see that it's co-rotating with the planet. And we understand how polygons and waves sort of conform in rotating tanks. And this is like a simulation here on the right. And one paper that I was on with my advisor, we simulated the hexagon. And we were simulating Saturn's atmosphere near the North Pole. And depending here on like the conditions underneath the clouds, we could either get it or not. So what's interesting is on the very left, we didn't have any vertical wind shear. So the wind was constant with height. And what happened was the jet that was there turned into what we call a vortex stream. Just signs like alternating cyclones, sort of like what you see in Jupiter, right? They have 8 cyclones up there or 5. So you get a pattern that just shows individual storms, not a continuous wave. In the middle here, we started messing around with, okay, well, what if I change the rotation rate and maybe have a little vertical wind shear? Well, it starts to look like something like a hexagon. But remember, one of the criteria or one of the things about the hexagon is it looks like it's co-rotating with the planet. So what we tried to do then was mess with that vertical wind structure to get this pattern speed to be like vertical. And so that on the right there shows you that that pattern of the hexagon is stationary. And what we figured out to do was we changed the vertical wind, or we changed the wind speeds with latitude underneath. And it was purely from modeling that we figured out something about what could be happening underneath the clouds to show us what we see from the clouds. And then some other interesting things that we only saw from the Cassini mission was that at the North Pole, I mean, this looks like something going down a drain in your bathtub. There's a polar vortex at the North Pole. There's a polar cyclone and vortex at the South Pole. And actually at different angles here with Cassini, you're actually able to measure the top right picture from the shadows. You can see and estimate how high these clouds are. And, you know, this is basically like when you think about a hurricane and an eye wall, like that's almost what we do sometimes. It's like, oh, how high is this? Okay, so I told you guys I was gonna maybe end with a little preview of something about Uranus. You are maybe the first people to see this other than like my collaborators. I sent this to them on Tuesday. So over here on in panel A, when Voyager 2 flew by Uranus in 1986, it found this like polar cyclone at the South Pole. The seasons on Uranus are 20 or 40 years long. I'd have to check. I think it's 40.
4-year period.
40, yeah,
Orbital period is 84 years.
84 years. So 20 years. So, okay, so we go later into the equinox and, you know, 2008, 2011. So now because Uranus is tilted like right on its edge, we only could see like the like low latitudes in the equator. And you could see all these little storms and stuff there. But we could never see the North Pole. The North Pole right now, this bottom left panel here, is coming into view. And that's an image from the Hubble telescope 2 years ago. And we're starting to see a polar cloud form over the North Pole. And so my proposal is saying, all right, in this cycle 11, before the solstice in 2030, is there a polar cyclone there? And I want to use the ALMA observatory, which is in Chile. It's an interferometer, much like the VLA, but different wavelengths. And a friend that I know and a colleague, he actually saw it. There's evidence from VLA data in 2021 that there's a small, bright, compact source right at the North Pole. I don't know if you guys make that out. And the thing about the VLA that I told you before is the VLA is sensitive to deeper down in the atmosphere. ALMA is different frequencies, so it's higher up. So the question that we have for this proposal is, are these polar cyclones something that are permanent and deeper in the atmosphere and propagate upwards? Or is it something about the seasons that change the upper atmosphere and then allow the polar cyclone to form? Because we saw a polar cyclone when Voyager flew by, but we don't see that evidence of the polar cyclone at the high cloud level yet. So why not? Is it just taking time to get up there, or is it maybe not there yet? That's the crux of that proposal. So, you know, fingers crossed. And yeah, so oh yeah, right. Oh, so my last slide is like, thank you. But I also say, like, I take pictures and look through telescopes that are not in space or cost billions of dollars. And this is a picture of the bottom left. There's a picture of me, and I don't know what that. Looking at the Jupiter and Saturn conjunction in 2020, right? The Christmas conjunction. And this was not from this last eclipse. This is from 2017 when we were in Wyoming. And so you can see the diamond ring there and then the time lapse that my friend and I like stitched together. And I just wanted to say, like, I went to Buffalo for the eclipse, and it was really cool that it got really dark. And we saw the sun and the disk a couple times, but I feel like missed out on that. So I hope everybody else had better viewing pleasure than we did in there, but it sounds like it. So thank you for having me, and I'll take any questions.
Things going counterclockwise when you were showing the pictures of rotations.
Where?
There's a few pictures back, but
Oh, yeah.
I was looking, there it is, counterclockwise and those.
Oh, yeah. So the orbit here? Oh, you mean these?
Yeah.
Yeah, because so Uranus is tilted. So Earth is like 23.5 degrees. Uranus is actually tilted like 93. 95, yeah, 93, 95. So this is just showing you the orientation of how it's rotating in respect to its orbit around the sun. And so right now we're more edge on, but as Uranus is coming into view and the North Pole is staring at us, we won't really be able to see any of the rotation because we're looking right down as it's rotating like this. So it'll be hard to measure stuff.
How is north, how do you define north pole? What?
By the direction of rotation.
By the direction of rotation, or also you just right-hand rule, right? But depending on how you define it, Venus and Uranus are odd in that respect because, well, oh, maybe Venus like rotates slower than it orbits. So if you chose one way to define it, it's counter rotating, right? And this is sort of like with Uranus too, because it's just so extreme.
And if you're looking down over a North Pole, it needs to be going counterclockwise plus theta direction.
Mhm.
So that's, no matter where that North Pole is, north or south of the ecliptic.
Yeah, that was actually something, as Voyager was going to Uranus, there are papers before the 1990s and maybe like 2000 that actually said that was the North Pole because like the definition wasn't sort of, I guess, converged on. And so there's some interesting things like now this is the North Pole. So
So is that also the other rotation question was the cyclones and anticyclones? Is that what the direction of rotation is related to that?
yeah.
Okay.
Yeah, so if the vorticity, if it's anticyclonic or cyclonic, depending on which hemisphere it is. Trust me, like when I was doing this for my PhD, that I had cheat sheets about eastward winds and westerly winds and cyclonic shear versus anti-cyclonic, yeah. Were there any questions
I
on
thought we were
that?
gonna touch on Neptune a little bit because there wasn't a whole lot of weather about.
Yeah, I, to be honest, I just didn't have time to put something here about Neptune. I'm studying Neptune right now. The Neptune has the great dark spot that we saw from Voyager, but that spot only lasted about 3 years. A new great dark spot or dark spot emerged like 2015, and again was gone in about 1.5 years. So these dark spots that are appearing on Neptune, we don't see anything like that on Uranus. And so the question is why? Is it from the tilt or is it energy? Neptune has the fastest winds in the solar system, and it's the furthest planet from the sun. 700 meter per second wind differential but Jupiter is only about 150. So it's really interesting. We don't understand exactly why that is. Yeah.
That on the North Pole of Saturn, is that a cyclone on the North Pole of Saturn?
It is.
Wow, it is really interesting. And then
Yeah,
they
that-
used it to figure out the cloud heights.
Yeah, and that was for the South Pole. They figured out the cloud heights of the cyclone here.
That's crazy, that top right one.
Both the North and the South Pole both have cyclones.
Yep, and Venus has cyclones too at its poles.
Does it have a anticyclone or high pressure system on Saturn?
No, and this is one of those things that we just have pictures. So we can't, it's not like we're measuring the winds and see the motion there, but we're just getting a snapshot of the picture. So a cyclone you would imagine would, have this converging air and downwelling in the center and convection at the sides. But we don't have that sort of like evidence like we do with like drop sounds from planes flying through storms here. So a lot of it is inferred just like, all right, the dynamics say this has to be cyclonic, or the dynamics say this has to be anticyclonic. So the dark spots, or those, I don't want to go all the way back, but the spots that we see on Neptune, if they're coming from deeper down and they're coming up, they got to be anticyclonic to conserve angular momentum. So they have to be diverging outwards because a hurricane is coming in and going down. So we've seen that, but that really, we don't have a good explanation of why that happens. And so why are these storms or these like spots that are appearing on the giant planets, how are they driven and generated? And what drives them to be anticyclonic versus some of the stuff that looks like hurricanes? What's driving these things to be cyclonic?
Oh, that is really interesting. That does look like water going on the drain. This to me looks like,
Yeah.
ripples in a pond of like a rock was getting thrown in the water.
Mhm.
And on the one on the upper right.
I mean, the size and scale, I can't even imagine Earth is probably could fit in that hole.
Oh, yeah. Yeah.
Doesn't it look like ripples in a water like rock was thrown in?
Yep.
I mean, I could only imagine if we were, yeah, on a planet that's 100 times our size, and it's also or rotating
10 hours.
every 10 hours. I'm
Yeah.
like, the atmosphere would, be a little thick and
Yep.
weird.
So I wish we had more time. I would talk about weather on all the planets and everything, but this is a couple of highlights and tried to not have any crazy plots. I know there are some with arrows, but no math, a lot of pictures. So
We love math, and we love pictures more though. Thank you so much.
You're welcome. Yeah.
Arjun has his hand up.
Oh, sorry.
Yeah, sorry, I haven't been paying attention to online. So please go ahead.
Yeah, so I was wondering, how does Uranus's extreme tilt like affect the weather on it? And like, does the weather somehow mess with the magnetic fields because they're out of like alignment?
I mean, you just asked two multi-billion-dollar questions. So these are the exact questions that the Uranus mission is like the top priority for NASA going forward. So in the next 20 or 30 years, like your questions are hopefully answered. And yeah, that extreme tilt, the magnetic field is not offset. It doesn't follow the winds. The magnetic field is actually like sort of in between, and it's not a very strong dipole. It's actually a quadrupole, and we don't understand why that is. And so maybe you could think that whatever caused Uranus to be so tilted was maybe from a giant impact, and that disturbed the deeper inner atmosphere of the planet where the magnetic field is generated, and that's how it's all misaligned. But your questions there are very good, expensive questions that this Uranus mission is going to answer. And, if you want to get into it, I'd say you're primed to be somebody who's working on that mission, because the launch date, maybe at the earliest, is 2030. And you're not going to have arrival to Uranus until 2038, 2040 at the earliest. So 20 years from now, maybe we'll know.
You'll make it.
Okay. So another question in like similar like range to that, how does like a planet's magnetic field like directly affect the weather on it, but like not the space weather, but the actual like weather on it?
Yeah, I'm not sure there's a direct answer I could give you from this for like Jupiter or Saturn. Feel like the weather there is mostly disconnected from the magnetic field, but I feel like for Uranus and the induced magnetic field that is present on Mars, I know people that are studying that, and there are some correlations to how like large dust storms on Mars arise at certain points in its orbit and every couple years. And it seems to line up with, the magnetic field is a little weaker at this position in its orbit than later, and so maybe there's more solar radiation that gets down that could cause that. But that's another really great question, so,
Okay, thank you.
yeah, you're welcome.
Anybody else online? Sorry, I kind of got caught up in the room and forgot to ask online. Any other questions? Well, great. Thank you so much again. That was really, really fun.
Yeah, thank you.
And Jim Tomney in the corner there, who asked the other question about where you got your Saturn images. He's an avid Saturn photographer, I mean Jupiter photographer.
Oh, awesome.
So, but unfortunately, the weather does not allow Jim to take pictures every day.
For which my wife is very grateful.
Let's see if I can grab this now, move it.
Great presentation. Thank you.
Oh, thank you. I'm gonna get those names for you.
If I can only grab this and bring it back, well, whatever, I'll just leave it there.
Grab the screen.
I really need to get two computers in here for one for the Zoom and one for the meeting.
Victor, is there any way to get rid of those red lines? Or is that what you said you can't grab it? Online, we have some red lines and green, there's even a small green line that got onto our screen.
Oh, was that?
Yeah, no, you didn't do it.
Oh.
Let's see. We're looking for a button that says like clear screen or clear annotations. Maybe,
Yeah.
maybe click here. Yeah, can I?
Yeah, please.
Oh,
Sorry.
You just put the eraser.
Is Richard still there?
I am, yes.
Hey, was the site you get your images from, is that the Alpo Japan site?
Eight
It's not.
Alpo?
Is it the Alpo Japan?
Yeah, ALPO.
Yeah.
That's it.
Yep. Okay. And yeah, Shinji, is he one of the guys you get the images?
Let me just close PowerPoint.
Probably Chris Goes and Shinji.
Yeah, Chris, yeah.
Yeah. Yeah, I post a lot on there too.
Yeah, I have the specific names here. I'm gonna put it, I'll send you an email or in the chat later.
James W.
When in doubt, just shut down and reboot. I just closed.
Hey,
PowerPoint.
Victor.
Yes, sir.
Yeah, look who made it online tonight.
I'm very happy to hear your voice.
I think the squiggles are on Zoom, not.
Oh, they're on Zoom.
Yeah. it's-
They're Zoom squiggles.
Yeah. Yeah, I'm thinking they are
they still
Zoom
there?
squiggles. Yeah, I still see them. Am I the only
Yeah.
one that see them?
The toolbar.
No, I see them too, Wayne.
Okay.
Me too.
See this bar on the left-hand side?
Me too.
There's like an eraser icon.
You have to move your mouse to the side. Ah, there it is.
Down.
I think.
Yeah.
Yeah.
Yay.
See when you know.
Thank you.
No, there's one more green spot.
too. On the
On the
left
on the
side.
wings, on
I
the
can-
people in the
yeah,
room.
there you got it.
All right, is everybody good now?
Yeah, I'm happy. Thank you.
Wow, I thought I was anal.
Got a little green line in the center.
No, there's still the green line right in center of the way.
All right, that's good.
How did they even get there? Was somebody online messing around?
Yeah.
I think the drawing tool got touched on.
All right. So, I guess I'll just leave this thing here and, go back to PowerPoint. Thanks for that. Whoever figured that out. Oh boy, here we go.
That's right.
Okay, so now we are, what is that?
I think that's a February.
I opened the
That's the wrong
wrong, I
one.
opened the wrong PowerPoint. Oh, yeah. What a mess. First, the star parties was in June, now the meetings are in February. All right, I think I got
Probably my fault.
Sorry about that, folks.
Yeah, it's my fault.
No. All right, that's the right date, right? All right, so now we move to the next part, which is what's out in the sky this month. And so, Jim, I will flip for you, but take it away.
Alrighty. Well, you already touched on this earlier, Victor. We have the Lyrid meteor shower going to be happening this weekend. But as you mentioned, we've got a full moon to go with it. So, that will certainly cut down on stuff. I don't know that you have to be up at 5 a.m., but certainly like midnight or after is good. This one, the one thing that might be enticing to get you out there would be this one tends to throw fireballs on occasion. I remember, I think it was 2 years ago, I was driving home late at night during this and actually caught a very nice one from the Lyrids. So you might want to put it on your calendar if we have good weather, kind of get up and take a look. You might be rewarded with a really brilliant meteor. Next. So unfortunately, we're getting into a period where all of the planets are really not well placed for observation. Jupiter, if you came out to the public star party, you saw it's really getting pretty low. When they get low like that, you got to deal with weather, the atmosphere, it's really not as good. So the planets in general right now are challenging. Saturn and Mars are in the early morning. Venus is very close to the sun. Jupiter's getting closer to its solar conjunction every day. So not a whole lot going on there. So given that, let's go ahead and maybe do something. Oh, yes, definitely stay on the alert for this once in an 80-year occurrence. There is a star in Corona Borealis, which is a spring constellation. So it's getting into good position. And there is a star there currently around 9th magnitude, roughly, that about every 80 years does an explosion and actually goes up to about 2nd magnitude or thereabouts. So keep an eye out on your email. Be sure that you're subscribed to the HAL list. And if that comes about, it'll only stay that bright for a couple of days. It's not like a supernova. But it'd be really cool if we have clear skies and you can catch that.
So not bright enough to see during the day, but easily with your eye, your naked eye.
Yeah. So I thought what we do is just, when we don't have much planetary stuff going on, some of the brighter objects out in the sky we can call shallow sky because you don't need a whole lot of equipment to see them. So a really wonderful early springtime object, something that to me always means spring is coming, is the globular cluster M3, Messier. M stands for Messier. It's a catalog of some of the brightest deep space objects that Charles Messier mistook for comets. He was a comet hunter, and when he would find one of these things, it would be like a little fuzzy thing in his telescope, and he would make a note of it so that he wouldn't get fooled another time when visiting that area of the sky. Next. So what is a globular cluster? It's a large group of very old stars that are closely packed into like a symmetrical round ball of stars. They are the largest and most massive star clusters around. Next. So for M3, it's got about 500,000 stars in it, 500,000 stars. And that sphere is roughly 180 light years wide. It lies about 34,000 light years away. You might think that there are collisions going along in the center of that, in the core, But while the stars are much closer than we have in our galactic neighborhood, they're not really colliding. Although in some globulars, they have actually, I think especially M15, they have seen where they think some of the star, one may have passed by another, taken off some of the atmosphere and created what they call like a blue straggler. So very, very interesting objects. Next. So if you want to find something in the sky, you have to get oriented. So the first step here is going to be go outside one evening in the spring here and look, look to the northeast. And as you look up, you should be able to recognize the Big Dipper. Next. So if you follow the curve of the handle, you'll come down to a very bright orange star in the northeast. And that's called Arcturus in the constellation Boötes. And the acronym for that is that you arc down to Arcturus. Next one. So now once you have those two things as like landmarks between the Big Dipper and Arcturus, you'll see a star. It's about second magnitude called Cor Coralli, and it is the brightest star in Canis Venatici, the hunting dogs. So your objective is to find Arcturus and then find this other star, which is not super bright, but certainly should be visible even in light pollution. Next. And from there, you basically want to kind of draw a line between Cor Coralli and Arcturus, and roughly midway in between, you're going to find M3. And you could go ahead and click again, Victor. You could even find this in a small scope or even binoculars. In a small scope, you should be able to see that the round glow, it's not uniform. The larger the scope, the easier it'll be to see that there's like a core to this thing. It gets brighter as you head towards the center. And that's because you have more of a compact number of suns there. Next. In a larger telescope, like 6 inches and up, you'll begin to actually resolve some of these stars. And especially if you use averted vision. Averted vision is not looking something directly, but kind of like off to the side. You'll find that you'll be able to pick up fainter objects. If you have a larger telescope, like a 10-inch or so, and you look at this, you definitely should be able to pick up some of the brighter members of this cluster. And it makes a really impressive appearance with this glow and then like buckshot of stars scattered across it. Next. And of course, the appearance is going to be impacted by how dark your skies are and how large your telescope or binoculars are. But like I said, even with a pair of binoculars, you can go out with a pair of 7x50 binoculars and you can scan that area. And if you look carefully, you should be able to see a very small, tiny little round cloud, which is M3. And here is what it looks like through my 80mm refractor from light-soaked, light-polluted Towson. And there's a very beautiful sketch from Richard Orr of what it looks like in his 6-inch refractor. So get out there if you're not familiar with the night sky, learn about Boötes and the Big Dipper, and see if you can't track down M3.
Thanks for that, Jim. That was cool. I think I might actually go do some binocular hunting for it. Thanks for the star hopping tip.
Sure.
Okay, so next we move on. Did anybody have any questions for Jim or comments on all that? I often wonder, does anybody know if there's a resource or a website? I often wonder what it would look like if you were on a planet orbiting one of the suns in a globular cluster, like what the night sky would look like just how many stars and how bright they'd all be. I don't know if anybody's done that simulation.
I'm sure that, you know, we've had space artists depict that. I think I've seen one or two of what that would be like. I mean, basically, if you're in a planet there, you wouldn't have any night. It would be constant day.
Yeah, read Nightfall by Arthur C. Clarke.
Okay. Okay. That sounds like it might be even earlier than Crystal's book that she mentioned earlier on the planet?
Yeah, considerably. I think goes back to the 1950s. It's a short story.
Okay, cool.
Really good one.
All right. Maybe we should have a short story segment because I have a favorite one called by Isaac Asimov called The Last Question. Anyways, let's move on to members' astrophotos. So there were so many pictures I couldn't resist. Jim is going to talk a lot more. Whoops. Jim is going to talk a lot more about people's experiences and people's photos. But I wanted to provide a snapshot. James, I don't know if you were on earlier, but I focused on a couple of your images that were amazing earlier on in the presentation. But for now, I just wanted to give a quick kind of overview of some of the variety of what different places and different types of scopes that and different results that people got from this
That
eclipse.
prominence was spectacular.
Yeah.
Yeah, that was like literally, it was like you mean James's one earlier?
I mean, I saw it with my own eye.
Yeah, this guy here,
We were all blown away.
that guy right there.
Yeah.
Yeah,
Yeah.
he was incredible.
I was telling everyone to look, you could see through it.
Do prominences, are they male or female? Does anybody know? No. All right, well anyways, Jim will talk a lot more about this next month, so I'll just move on. So we have on our Discord group, we have the object of the month. This month it was IC 443 or the Jellyfish Nebula, and we the folks who are in that group take pictures and we all vote at the end of the month. And it was a tie this month, so I thought I would put both of them on.
That's awesome.
That is
Yeah.
beautiful.
It really is, and it's amazing. Like obviously they use different, just how different. Both of them are sharp and beautiful. It's just amazing how different they look with the different filters that were used and whatnot.
It looked like it could have easily been the same photographer,
Yeah,
the way they colored.
yeah.
They so pretty together.
Yeah, really. I like to call this the barfing frog nebula, but next we have Harini. Harini, are you online? This is Harini's very first astrophoto that she's ever submitted. And
I helped her get that line.
It's the moon. This is the waxing gibbous moon. I took it at the public star party. I used 114 LCM telescope and Celestron telescope, and I took the picture in an iPhone 13 phone.
well, this is a fantastic first astrophoto, I must say. Yeah. And the dedication, I don't know what you're doing, but you're obviously very dedicated on the ground there, looking. Good job.
Yeah, very nice picture.
Thank you.
And then we have Dan is in the room. Dan, you want to talk about your photo?
Yeah. Why don't we turn the light off so you can see it better? Let's make it off.
Just briefly tell us about how you took this picture.
There we go. That's much better. Well, I was at my oldest stepbrother's in New Jersey back in I want to say first part of March, and I captured an image of this Leo the line, the backward question mark Leo the line in Gemini, and I captured these faint stones in the Y that's capped to the crab. I just managed, and I put it on night mode, a few second exposure, and then I adjusted the sharpness, and it made the stars in the constellation sharp, and that's how I got the picture. Do you see the Y-shaped star?
Yeah,
That's the crab. So I managed to get it all in that picture.
Nice. Very nice. And that was with your phone?
Yes.
Nice. Very, very nice. Thanks, Dan. And then we have Dan, the other Dan Lohan. Are you on? Are you online? So he had a nice story about these and why he went out to Joshua Tree. And I don't have the details, but it was a pretty cool reason for being there. And it looks to me like he may have taken this picture like looking south and then turned around and looked north. You can sort of see the Big Dipper in this sky. And that looks like Orion there. So I thought these were good. He also said these were single shots that were just taken with I think a one-shot color camera. But then he sent this one, and this is my last slide for the day. He went, for any of you know the double rainbow meme, I'm sure he was very excited about the double rainbow. So he caught an amazing picture. So really, that's all we have for today. And I really appreciate everybody coming out, and I'm super excited about the club and the hobby and next month's meeting with Jim. And then we have some very, very interesting speakers in the next month thereafter, including I think I'll send it out again. We got some really interesting speakers for June, and they have a podcast series called Cosmic Visions. I'll send out a link. I've been listening to them. They're fantastic. It's worth listening to. So again, thank you to our speaker, and thanks everybody for coming out to HAL. I really appreciate it.
Great presentation.
And we can stay in the room for a little while if anybody wants to kibitz. We have some swag up here. I want to get some. And I'm gonna stop the recording. But I'll leave the Zoom meeting on in case if we want to kibitz here.
Yeah, so next month, no speaker, just everyone's gonna talk about their experience.
Led by Jim.
Oh, okay.
Bye, everybody.
I gotta get my picture.
Bye, Wayne.
Once in a while.